Okay, good afternoon, everyone. Sorry for being a little bit late today. Okay, so we're going to just pick up where we left off last time. There was some topics in the charging infrastructure that we didn't quite cover, so I'm going to quickly go through that before we start our main lecture for today. Okay, so rounding out our discussion last time on charging infrastructure, wanted to cover kind of the economics of it. So this is a table that gives kind of a high-level overview of the costs associated with installing a charger. Okay, and so if you remember L1, that's just like the thing that you can plug into your wall. Very generally pretty cheap. This particular table is like a conglomeration of data that a couple researchers had looked at for figures published on the cost of this hardware. So level one, pretty cheap, usually on the order of like $100 or cheaper. And then level two is going to be kind of on the order of a couple $100s. So most, you could go on like Amazon and you can find these like level two chargers. Pretty reasonable ones are going for like 400, 500 bucks. The reason why you see a high end here for like $1,200 to $2,000 is because there's actually additional installation costs if you need to upgrade your panel, right? And so when you own a home, you have your electrical panel with all the breakers in it, and you are given some capacity essentially from the utility for how much electricity your house can use. Most modern day houses get like 200 amps, and that's usually more than enough to include like an EV charger. But if you have an older house, you might have like 100 amp or even sometimes even a little bit lower than that, might require an upgrade. And so upgrading your panel can cost a little bit more money. You got to get an electrician to come in and do that. So that can actually boost the cost of installing, even if the hardware itself is only a couple $100s. You'll notice that for commercial, it's on average going to be quite a lot higher. And so why is that? The equipment is going to be pretty similar in terms of the service that it can provide, right? It's both level two, so you're getting like 6 kilowatts of charging, up to, let's say, 12 kilowatts on average. Well, a lot of the commercial equipment, that might be outdoors, right? And so it needs to be weatherized. In other words, it needs to be able to withstand like the elements, wind and rain and that sort of thing. So that can be a little bit more expensive. But the big one is often having to do with like the actual installation of the charger. So a lot of the ones you might see out in public, they might be in a parking lot, right? And so you need to actually do some trenching to run conduit out there as opposed to just sticking onto the wall of a garage. And so that's where the costs tend to be a lot higher for commercial. And then DC fast charging, all of that equipment that I talked about last time, having to have, cooling for for all the equipment, the converter to go from AC to DC, and then all the equipment associated with these like higher voltages, higher amperage, that's all going to cost quite a lot more money. And so here you can see ranges, depending on the speeds that we're talking about, you're usually on the order of like $100,000 to $200,000. I will say there's actually a lot of variation there. So Tesla famously has much lower costs for installing their chargers. One thing you guys can pay attention to if you ever go to a Tesla charger. So actually, let me go up to the next slide so you can see. There's a whole bunch of basically stuff that needs to get installed to put in a DC fast charger, right? And if you look at Teslas, you'll actually see, for example, the chargers are on these prefabricated like concrete pads, right? So they actually have everything kind of prefabricated. They could just essentially deliver it and drop it into place. Whereas a lot of other chargers are doing construction on site. They're like digging, trenching, they're pouring foundations. So you can see in terms of the like manufacturing process, Tesla is probably a little bit ahead of other companies. Other companies are starting to do similar things. And then also, the power distributor and load center is in like one centralized large location for Tesla chargers, whereas a lot of other companies, each charger has their own sort of load management system. And so distributing that out to sort of many chargers can cost a lot more money. And again, that's why, Tesla has these much larger stations, and then on a like per charger basis ends up being a lot cheaper. So, this is not an electrical engineering class. We're not going to like go through all the details of this stuff, but the idea is that if you have a site that's essentially ready to go, there's this term we call make ready, which is all of the infrastructure you need that's sort of upstream of your EVSE, right? And so this is your power distribution, your meter, a transformer, and then going out into the grid. Depending on the particular properties of your charging station, some of this stuff might differ. And then who pays for what also kind of depends on particular situations. But in general, the meter is kind of the dividing point. So everything upstream of the meter, like everything going towards the grid, is paid by the utility. And then everything downstream of the meter, going from the meter to the charger, all of that is usually paid by whoever, is the site owner, whoever's deploying that infrastructure. So the costs can vary quite a bit, as I've been mentioning. So this is a particular schematic of an actual charger installed on highway, I think it's on 99. So Caltrans, the California Department of Transportation, they funded and installed a bunch of chargers at rest stops throughout California. And this is one of the schematic diagrams. And so actually one of my students did a big study of these rest stop areas and actually found that the cost of installation was much higher. In fact, let me jump ahead to this slide. Yeah, so this case study. And so I was just mentioning that, the charger is usually like $100,000 to $200,000, depending on specific circumstances, right? But actually we can see balloon as high as, $500,000 in some cases. And so to go back to this particular example to show kind of why, kind of hard to see, but if you look closely, here's like the parking lot area of the rest stop. The utility provides a service drop all the way up here. And so you have to actually run conduit for like 100, 200 yards, right? Something like more than the length of a football field, where you have to essentially bring in construction crews, dig a trench, lay out that conduit over a long distance. And that can really add to costs. Yeah, and so again, the sort of unique circumstance of individual stations leads to a pretty wide distribution of costs that we observe for these things. So it's not so easy to just say, oh yeah, like a DC fast charger costs like X dollars. Depends on a lot of other factors. Yeah, and so if we want to think about costs from the perspective of policy, like what's the right approach to maybe like subsidizing a charger, right? Like how much money should we actually put forth to, support, especially given the sort of heterogeneity in the costs that we observe. So this one is maybe a little bit outdated at this point, but there was a bunch of analyses that were kind of looking at, if we were to meet 2030 goals, both like California-wide and nationwide, how many chargers would we actually need, and kind of what would that cost? And so there was some analyses kind of done on looking at this. And so whether that funding is coming from the public, right, from government subsidies, or if it's like private companies who are installing chargers, the total cost is kind of looking on the order of over $100 billion to get all of that infrastructure in place that we need. And then in terms of the actual number of chargers to meet those 2030 goals, that would look something like this, right? So we would need something like 180,000 DC fast chargers that are used for slightly different cases. So corridor charging, to connect highway networks. Community is more kind of local stuff, and then there's even kind of this analysis that includes ride hailing. So special case, we're not going to talk about too much in this class, but folks who drive for Uber and Lyft that use electric vehicles, they actually have a very high demand for electricity, and they're often using public chargers disproportionately more. So there's some kind of carve out in this analysis for them as well. And I mentioned outdated because these goals that we're talking about are really connected to a lot of policies that were put in place earlier on in California or by the sort of Biden administration. And so there's projections of like how many electric vehicles we need to be on the road to meet those targets. But obviously those targets have maybe since changed with the new administration. So whatever those 2030 numbers are that were projected in these analyses are probably a little bit lower now, given that the targets have changed. Okay, what's the business case for EV chargers? So we just talked about the cost of these things, right? And so for like a DC fast charger, that might be something like, okay, if I was a business, right, and let's say I'm a restaurant and I have this parking lot and I'm like, oh, I'd like to install some chargers so that people can charge and I can maybe make some money, right? And so paying all of that, paying that money up front versus how much money do I get back from getting people to charge at my charger. So we did this analysis where we looked at businesses that might want like a 3 to 5 year payback period. And even under pretty optimistic assumptions, it doesn't look all that promising, right? So this plot here is, kind of like a punchline figure. This on the x-axis, this is how many times someone would visit the charger in a month. And then this is how many times, or how long basically you spend at a charger, how many miles they're charging up on. Right, and so the more people visit and the more people charge, the more sort of positive in your payback you are. And then this line kind of represents what you would require to get a 3-year payback period. And then this dot is actually where we are today in terms of how much DC fast charging gets utilized on average at a particular charger. So it's not very promising as a strictly financial investment. If you're trying to make money installing a charger and selling the electricity from the charger is probably not the best sort of business investment. But that's actually okay. So can we think about alternative revenue sources, right? So for gas stations, there's actually kind of a similar story in that you don't actually make that much money from selling gas at a gas station. So most of the revenue might be from selling gas, but the actual profit comes from other places. And so what might that be? Actually concessions, right? So selling candy bars and sodas and chips. That actually provides most of the profit for gas stations. For EV chargers, right, we're not actually seeing very much profit from electricity sales, right? You might be making, a couple bucks a minute every time someone's charging. Um, but what are the sort of alternative revenue sources? So this is an example of a charger located in LA, and then within like a 5 to 10 minute walking distance, what kind of services are located nearby? So you've got restaurants, grocery stores, hotels, movie theaters, all of these sorts of things. So the idea is actually chargers near services not only see more visits, um, but when you have a lot of these amenities nearby the chargers, um, yeah, you can think of those as kind of the same way we're thinking about sort of concessions in a gas station. Uh, you might be able to bring in extra revenue, more kind of feet in the door, right? There's a there's this kind of business case statistic. They say, like for a Target, for every 10 minutes that someone spends in Target, they spend on average something like $15 to $20 more, right? And so the idea is, can we translate, these uh, additional business revenue into kind of supporting, local infrastructure? Yeah, and so in addition to that, there are some really fast chargers that are thinking of a similar kind of thing to a gas station model, where you have these charging plazas that have similar amenities and services to what you would find at gas stations. Okay? Any questions about any of this? Okay, one last thing on infrastructure. So we have mainly been talking about sort of modern charging infrastructure as we see it today. There are some kind of interesting things to think about with different ways of charging your vehicle. Okay, so the first is wireless charging. I get asked about this a lot. So this is inductive charging. You're basically using electromagnetic induction, which generates electricity through inductive coupling. So if anyone ever uses like a MagSafe charger on their iPhone, right, this is essentially the same thing, but with a car. There's a magnetic field that's generated that induces AC current in an induction coil in the vehicle. So no modern vehicles today actually have this built in, but it is kind of a possibility to think about doing this. It's not theoretical, right? This is totally something that exists and works, especially in other contexts like phones. But it is more expensive than your regular chargers that we've been talking about. And there are some technological barriers as well, right? So if you think about the gap that needs to happen between the wireless charger and your vehicle, the amount of power and efficiency is actually a function of the distance squared. And so you actually have to get pretty close to get an effective charge with the vehicle. But sort of there's nothing you can really do to avoid some of the inefficiencies, right? So this will always be less efficient than charging with a cable. There's kind of two types of wireless charging. There's a static version and a dynamic. So static is, you can think about these like pads that might be, mounted under or in parking spots. So you just drive over it and your vehicle will start charging. That is if automakers actually decide to build in the capability to do that at some point. And the other is dynamic wireless charging. And so you may have heard of like this idea that we would put these inductive chargers kind of embedded in the roadway so that you can actually charge while you're driving. So there, you've got a lot more technical difficulties, and I have never seen like a case study of dynamic wireless charging that is even close to economic, right? So you're talking about on the order of like tens of $1 million per mile to do this. Yeah, so generally speaking, I'm personally a little bit more skeptical of dynamic wireless charging. I think static wireless charging might be a thing in niche applications. You know, if you just want to, you know, install these things in certain locations where it might be inconvenient to have a charging cord. But generally, I don't think it's going to be all that popular. But I could be wrong, so we'll see. Okay, the other big technology is battery swapping. So instead of taking all the time to like charge up your battery, the idea is let me just pull into a station, it'll yank the battery out of my car and just put in a fully charged one. And so the idea is to overcome some of the limitations that people feel are particularly prevalent with electric vehicles, right? Which is the sort of long recharge time. There are technical issues, right? No automakers in the US at least are making battery swap technologies very accessible. They are built into the body of the vehicle and are not easily removable. And so you would need at least one or more automakers to go on board with this and redesign their vehicles to allow for battery swapping in the first place. And then secondly, the economics of having more and more batteries to provide this service, I've also not seen a great case for this either. So, you know, it's kind of like this rocket ship problem. You need some number of batteries to be able to sustain people coming through, right? But each battery costs a lot of money. And so if you want to make that money back, you need more people going through your station. But if you have more people going through your station, you need more batteries to sustain it. And so, yeah, the economics of this are also questionable. I will say, however, battery swapping is not like a totally pie in the sky thing. So in China, for example, there actually are implementations of like commercial battery swapping, particularly in the heavy duty space. So they have these, you know, large trucks, and yeah, you guys can look up some of the videos of how they do the battery swaps. But it is and has been implemented in China, and I think there's one or two automakers who have actually are pushing more towards battery swapping in China, and they have a couple stations, but it's not quite as widespread as the sort of typical charging that we've been talking about. I think there some of the economics are supported by, you know, government subsidies, so that does change the equation a little bit in terms of cost. Okay, any questions about battery swapping? Okay, and last one I'll talk about, it's kind of interesting, this idea of automated charging. So this is kind of like a in-between type of thing where for wireless charging, you have to like position your car in a very precise way in order to get a good effective charge. And so there's some companies have been thinking about ways that you can automate like the actual cord-based charging, right? And so this is an example of like charging, using an automated charger to charge a Tesla. This is not as wacky as it might seem, one of the ideas, right, is, I was talking about the cost of installing these chargers, right? It can be quite high. Imagine that you are in like an apartment complex, right, with a lot of parking, but not so many chargers. Um, Instead of trying to install a bunch of low-speed chargers everywhere, or spending a ton of money on installing, a whole bank of level 2 chargers that won't all be sort of accessed, the idea is this could actually be a more economic and efficient way of doing things, where you have one charger that can like move around in the parking lot, right? Particularly, if spaces aren't assigned, or you have to do a bunch of sharing of the EV chargers across more EVs than there are, chargers that exist. It would be a pain if you're charging your car at night and then you have to like get up in the middle of the night to unplug so that someone else can use it, right? So the idea with something like this is you could have these like mobile chargers that could go around and charge vehicles without any sort of human assistance. Okay, to sum up, infrastructure, home is by far the most prevalent. It's the most convenient. But we do have this issue that there are populations, right, that don't necessarily have charging capabilities. So think about apartments and condos, or people who have to park on the street. And so there's a big challenge to bridge that gap and provide home charging for those populations. We still need public fast charging, and we talk about issues with reliability, and then just now with the sort of costs and business case. We haven't, I guess we touched on this a little bit, right? But the relative difference in costs of charging is shrinking because of high electricity prices in California. Maybe that's a little bit different now with gas getting a little bit more expensive in recent days, but generally speaking, electricity is still cheaper, but that gap has decreased quite a lot over the last couple of years because of high electricity prices. And then we talked about the whole issue with the connector standardization, right? There's this big movement towards the NACS or J3400 standard, but that hasn't been fully standardized yet, and you have a lot of kind of sunk costs into stations that have deployed CCS. So I would imagine in the near future, there's going to be lots of adapters needing to be used so that people can kind of use both Tesla stations and our other stations that have deployed CCS connectors. Okay. Any questions about infrastructure before we move on? All right. So let's talk about vehicle production costs and total cost of ownership. So this is a plot of vehicle purchase price that we've shown before, right? And so there's this big gap between electric vehicle costs and gas car costs. So let's dive into what kind of makes that so different. Okay, production costs. So vehicles have been mass produced for over 100 years. Starting with kind of the Ford Model T, thinking about real production and assembly lines, and across all of this time, and then across this very competitive automaker market, the production process itself has been very refined, and many of the costs are pretty well understood. So let's break down what this actually looks like. Here are the different components of cost, and much of much of the costs associated with the production of the body of the vehicle are actually going to be pretty similar between an electric vehicle and an internal combustion engine vehicle or a gas car, right? So we look at, for example, the chassis, the body, exterior, interior. Most of these figures are going to be essentially the same. Where you have a big difference is in the powertrain, right? And so for a gas car, some amount of money needs to be spent on essentially manufacturing the engine, and then other parts of the drivetrain so excluding the engine. So this might be, your transmission system, drive shaft, and all of the things associated with the drivetrain. Meanwhile, on the electric vehicle side, you can see the sort of two big portions of the cost, right? This accounts for something like about 2/3 of the total cost are going to be in your battery and your electric drivetrain. So that would include things like the motor and the gearbox. And really, that's that difference, the difference between the cost of the drivetrain in the electric vehicle and the gas car is what drives the difference in total material cost between the two technologies. Okay, so vehicle production costs have gone down quite a bit over time. So this is a plot of production costs for Tesla. We can see, up at $40,000 down to about $36,000 by the fourth quarter of 2023. This plot is a little bit deceptive. It should actually be going all the way down to zero. And so the decrease is not as big as it looks here. You're talking about maybe about a 10% decline over the course of 2 years. Some of those costs actually have to do with reductions in production costs over time. But some of those are inflated costs due to supply chain issues during the pandemic. So this plot is known as cost of goods. So that's all the cost of the materials going into the vehicle. And then what does that look like for other automakers, right? Cost of goods for Volkswagen is about $30,000, for Toyota, $18,000. And that includes all the materials, labor, manufacturing costs, and so on, but doesn't include costs related to actually selling the vehicle. So like marketing, advertising your vehicle, or sales related costs. The approximate profit per vehicle, Tesla is now at $8,000 to $15,000 per vehicle that they sell. And not everyone, and these are specifically figures as it relates to the electric vehicles being sold by these automakers, not uniform across the industry. And in fact, Tesla for a long period of time wasn't making any profit on some of their earlier instantiation of vehicle models. They were able to survive via some of the regulatory benefits that they get from credits, which we'll talk about way later on in this class. Okay, but now they are able to be profitable, and we can see that even within a single automaker, that figure, this average figure, doesn't necessarily represent, the sort of individual profits per vehicle. So for example, Ford, they actually make some money off of their electric Ford F-150 Lightnings, but they for some period of time, were actually losing quite a bit of money on their Mach-E vehicle. Okay, so lot of heterogeneity in vehicle profit and rapid changes in profit over time. So we're going to talk a little bit more about this in a second, but the idea is, and I've been kind of hinting at this, especially with the battery economics, right, is that the costs of these vehicles are actually going to decrease over time. And there have been some estimates. So this is in a particular report by the International Council of Clean Transportation. They are kind of like this think tank that does work on sustainable transportation transitions. And they did this analysis that basically said, oh, when will price parity be reached? Price parity being when will an electric car and a gas car sell for the same amount of money? And so price parity on different ranges of electric vehicles kind of over time. Oh. Yeah, so going from 2024 out to 2030, yeah, some vehicles actually already are at price parity, and then longer and longer range vehicles, it's more and more likely that they're going to be kind of equivalent to gas cars pretty soon. There are some challenges with this, right? We've talked about the supply chain for battery materials, but just as a quick refresher, right? Higher reliance on international markets, and so things like having tariffs or trade wars with certain countries will certainly affect, these timelines and when EVs are expected to break even, right? We've talked about some of the humanitarian issues with using like cobalt. So certain materials are likely to be less stable over time. And then, environmental damages associated with some of these materials as well may lead shifts away from certain battery chemistries. And that can affect, the economics and the rollout of particular vehicle types. When we think about the actual cost breakdown of the battery itself, a lot of these costs can be difficult to measure accurately. A lot of this information is often confidential. It's not like these companies are openly sharing where they're getting materials from, how much it costs them, and that sort of thing. So there have been a number of studies that have tried to estimate what those breakdowns look like. But as you can see here, I pulled up a couple examples. The variation in the cost components is really large. So there isn't really great data for the cost of these things. But these categories are generally going to be consistent across different studies. And so you can look at this slide can be kind of a reference slide for you guys to see what portions of the battery have specific costs associated with them. Okay, any questions about these breakdowns? Okay. So costs are likely going to be coming down, as I've been mentioning. And so let's look at a couple of reasons why we think this will be happening. So one is economies of scale, right? So the more that you build, the sort of more economical your production process becomes. So there are cost advantages that will grow based on the scale of your operation, right? So if I'm producing 100 of something compared to 1,000 of something, compared to 1,000,000 of something, uh, the the amount of money required to invest in each individual unit usually will scale downwards. If I buy things in bulk, right, that's going to help with costs. You can have specialization in the production process as you have larger and larger production lines. Um, Financial scaling, that's a big one. So you imagine, if I'm borrowing money to buy a car versus if I'm borrowing money to buy a house, right, the interest rate that I get from the bank is pretty different. And generally speaking, um, the larger quantity of money that you're borrowing will usually get you sort of better interest rates. Marketing, so spreading the cost of advertising, right? If you're only selling 10 of something versus 1,000 of something, you can spread those costs out a lot more. And then in general, the ability to scale up to production more efficiently. So these are all things tied to economies of scale that will help reduce costs. And then there's a different concept known as a learning curve. So not to conflate the two. So economies of scale and learning curves are not the same thing. This is the idea that the more that you build it, the faster that you'll get at it. Right? So with more production, you will perform certain tasks more often, and every time you do it, requires kind of less time to do that production process. The example I've often heard is like if you have to build like 10 paper airplanes, right? The first one that you build takes the longest, and by the time you're doing the 10th one, you're able to do it kind of a lot faster. So these are labor efficiencies, so people who are just better at doing that production process the more you do it. Standardization, specialization, methods improvement, both will increase efficiency. You might be able to automate certain types of production once you're more familiar with the process. You might get better equipment that lets you have better production yields. And then you may figure out better ways to use certain resources or to design the product in certain ways that's going to be more efficient and faster and help reduce costs. This is not something that's unique to electric vehicles. Actually, for any new technology, for any sort of production process, we often have this sort of generic way of calculating what the cost decrease is going to look like as I produce more and more of something. So there's kind of this generic exponential equation that you can use to represent a learning curve. So generically, you have this y equals, A, so the cost of the first unit times the cumulative number of units produced, capital X, to the power of a learning rate parameter. So this is a way that you basically say, oh, how much does it cost for me to produce 100 units of something versus 1,000 units of something versus 100,000 units of something. And the units A, B are like calibrated to your particular technology. You could do this in like a simple regression, for example. So this is like this is a simple exponential decay function, and describes the rate at which costs drop as you produce more of something. So, for example, cell phones, they cost a lot at the beginning, and then drop over time as you produce cumulatively more and more of these. We can apply this to other technologies as well. So this is a linearized learning rates for solar PV, right? So you can see this axis here is not exponential. They've essentially linearize this curve. But as you produce more capacity of solar PV, the costs have decreased over time in this way. Okay? And the same thing can be said for batteries, right? So lithium ion, there's a learning curve here. The green is a comparison against solar PV, but the electric, the battery pack, lithium ion battery packs is in the blue down here, and as we produce more and more in capacity, we can see that it's following kind of a similar type of learning curve. Not all technologies have like the same learning curves, but most technologies you can represent with a learning curve of some kind. Okay. We've talked about decrease in battery costs over time before, and that looks something like this. Battery prices in the future are forecasted to continue to fall. And we can see what that looks like from 2024 to 2030. 2024 here to 2030 are forecasts. So this particular plot was put together a couple of years ago. But in general, we've followed this trend. For the most part. I guess right now, 2026, we're maybe a little bit higher. We're probably closer to 100 to 110 or 100, 115. So it hasn't maybe dropped off quite as fast as this particular forecast, but the trend has been definitely downwards over the last, decade and a half. Okay, any questions? All right, so I've been talking about price parity, right? The cost compared of a gas car versus an electric car when you purchase it. But actually now we want to think about something known as the total cost of ownership, right? And so when you go out there and you buy a car, that's not the only money that you're spending on getting a vehicle and then using it over its lifetime, right? You have to pay for, what are some of the things that you would need to pay for? Right, so buying the car, outside of that, you need to pay for fuel, you need to pay for insurance, you need to pay maintenance and repair, and you need to pay registration fees, right? And so all of these things go into that total cost of ownership. And so we need to think about how that compares in a gas car versus an electric car. So is an EV cheaper or is a gas car cheaper when we think about that full sort of lifetime of the vehicle? Purchasing the new car represents only a portion of the total costs. We care about TCO, right? Because you're not looking at just the cost of buying the car. It's essentially the cost of owning the car over its lifetime. And so I think the best apples to apples comparison for what's actually cheaper to own and operate is to include not only the purchase price, but all of these other factors. Okay, so what does this look like? So for a Toyota RAV4, and so I should mention there are like websites that you can look at. You can plug in a particular car and you can look at kind of the average ownership costs. So this is not a full lifetime ownership cost. This looks at the 5-year ownership cost. The depreciation you can think of that as kind of the amount of the purchase price of your vehicle that goes towards like the first 5 years. What's the value that you're getting in those first 5 years of ownership? So whatever you ended up paying MSRP for the RAV4, we're counting this number as kind of the value of the car in those first 5 years. You're likely going to pay something like $6,000 to $7,000 in insurance over the first couple years, and then you've got fuel costs here, $6,000 here. Maybe you finance the vehicle, and so you're paying off some interest. You have some maintenance. Maintenance in the first 5 years is probably going to look very different from maintenance over the full lifetime of the vehicle, right? It's less likely that you're going to have to do as much or as expensive maintenance at the beginning of the lifetime of the vehicle, but as you go on and the car gets older and older, that number may end going up. You have like registration fees and then repairs. Okay, so this is kind of this, again, little example of components of the cost looking only at the first 5 years. If you look at, on average, what does that look like across new vehicles in the US? The percentage breakdown looks something like this, where generally speaking, in the first 5 years, the depreciation or the like cost of buying the car apportioned to those years is the highest. And then comes the fuel costs, right? So operating the vehicle on a day-to-day basis, paying for gasoline, that ends up being kind of the second highest, largest components. And then you have things like interest and insurance and maintenance and repair. Okay? So let's dive in a little bit deeper into each of these components. Yeah, vehicle purchase price. This is an interesting one to think about. Particularly in kind of my world when we're doing research and we're trying to investigate costs of vehicles. Let's say I did want to do like a TCO analysis and compare EVs and gas cars. There are a couple of different numbers you may actually want to keep in mind, right? So there's an MSRP, there's a dealership listing price, and then there's a transaction price. The transaction price would be kind of the best thing that you could get in terms of data, right? If I wanted to understand a cost comparison, I want to know what people are actually paying for the car, and that would be kind of the transaction price. But that's not something that you can easily get in terms of just data. And so oftentimes we're relying on other values to proxy for what the transaction price actually would be. So one would be the dealership listing price. So if you were to go to a dealership and you like talk to a dealer or you look at the cars on the lot, you may see prices advertised on the vehicles. Or if you go to like a dealership website, right, you may see dealers advertising certain prices on their vehicles. And that may not actually be the final transaction price of your vehicle. Yeah, sometimes you can like haggle on these things and bring the prices down a little bit, right? And so maybe that's a little bit less common these days. But dealership listing prices often are going to differ a little bit from your transaction prices. MSRP is something a little bit different. for cars to have any sort of standardized price, you need some kind of baseline to kind of anchor that to. So actually at a dealership, like a dealer could sell their car for any amount of money that they wanted, right? They could set the price to, you know, $20,000 more than anyone else is selling it for, right? But the MSRP is essentially what the automaker suggests the car be sold for to a dealer. And then the dealer will kind of take that into advisement and decide, you know, based on local competition, based on other costs with like shipping the vehicle to them, all of these other things, they'll think about adjusting the MSRP based on their sort of specific context, right? And so sometimes you could have prices below MSRP, sometimes you could have prices above MSRP, and that depends kind of on the situation with the dealer, with the supply of the vehicle, and the demand of the vehicle, and that sort of thing. So, transaction price, most accurate, that's the best that you can do. Next is kind of the dealership listing price. And if all else fails, then the MSRP is going to give you at least some indication of the, you know, general level cost of that vehicle. Yeah, and so there is, as I've been mentioning, variation between these three different prices. Unless, for example, you're Tesla. So Tesla famously doesn't have any dealerships. And so whatever they sell their vehicles for, that MSRP is the price that you get. There's no negotiation or anything like that at a dealership. And so to some extent, people like that, right? Because, you know, most people don't like having to haggle for prices at a dealer. But I will warn that Tesla does change their MSRP of their vehicles pretty often. And so you could, for example, in November buy a car for like $50,000, and then in December they drop the price down to $40,000, and then you're kind of stuck out of luck, right? You paid $10,000 more than if you had like waited a month later. That was happening a lot more in the like pandemic era, as they were like really aggressively changing prices to respond to changes in the market. I think in general, those changes have been a little bit more stable in kind of the last year or two. Okay, any questions about purchase price? Yeah.
Why is the lag if this is the Model 3 and it goes up now?
Yeah, so I will say, so here, these are some listings of different Tesla models. So within a particular model, like a Model 3, you may have different price points depending on the size of the battery. And generally speaking, the larger the battery, the longer the range, but then the more expensive it is. And then across different vehicle models, like a Model 3 and Model Y, you're gonna have some differences in pricing as well. So SUVs, so Model Y is a crossover SUV. They're gonna be slightly bigger, and there are costs associated with the production of that might be slightly higher, right? Because it's kind of a bigger car. The other thing is that the market for sedans versus crossovers, there's been, I don't remember if I talked about this in this class, but it used to be like cars and trucks, and then SUVs became a new kind of category that really gained in popularity over the last 15, 20 years. And so it used to be kind of like a 40-40 split between cars and trucks, and then with a small, the remainder into, vans and SUVs and that sort of thing. And now SUVs sells more than cars and trucks, maybe even combined at this point. So because the demand is higher, they may try to price things a little bit higher to make slightly more profit on those as well. So the dynamics of why the Model Y is priced higher than the Model 3, one has to do with the cost of production of that vehicle is going to be higher, but two, maybe they're also pricing higher to capture the higher demand for those vehicles. Okay, good question. Anyone else? Any questions? Okay, so let's move on. So what about the next category? Fuel costs, our next biggest category. So we've got cost of charging the vehicle versus cost of filling up the vehicle at a gas station. Okay, and so how do we calculate the fueling costs over time? So calculating fuel costs for gas cars looks something like this. Let's say that an average car in the US is about 25 miles per gallon, and you have gas prices of $5 per gallon. How much would it cost to drive per mile? So I can do some dimensional analysis, right? So $5 per gallon of gas times the fuel efficiency. I put the gallons on top to cancel out the units. So it'll be $5 times 1/25. Gallon of gas cancels out and you get dollars per mile. So you would pay something like 20 cents per mile on average to drive a gas car in the US. And obviously that number can go up or down depending on the cost of gas and on the efficiency of your car, right? And so if your car is more efficient than 25 mpg, then your cost per mile will go down. But if gas prices are higher than $5 per gallon, then your cost per mile will go up. But this is in general how you might calculate it. Right, and so as an example of that, right, if I use the same cost per gallon, same cost of fuel, but a more fuel efficient vehicle at 55 mpg, right, I would be paying about half of what I would compared to the 25 mpg, right? So this would be 9 cents per mile instead of 20 cents per mile. And if you wanted to convert this into the total cost of fueling, right, you would just need to think about how many miles that you're driving total, right? So the average American drives something like 12,000 miles a year. And so you could convert that, right? So 12 times 12,000 miles times 20 cents a mile, that would be what, $2,400 a year you would spend on fuel for the average gas car. Whereas a Prius, you would do 12,000 miles times 9 cents per mile. What's 12 times 9? Like, so you're spending a little over $1,000, a little over $1,000 a year on gas, as opposed to $2,400 a year. Okay, what about for an electric vehicle? So we showed this chart last time, right? There's a lot more variation in electricity prices compared to gas prices, depending on where you live. Unfortunately, if we live in Davis, you pay PG&E rates, which are actually quite expensive right now, compared to Sacramento, which is like 3 times cheaper for electricity. Yeah, and these are all in dollars per kilowatt hour. So if I assume that I charge at home for some amount of time, you would use these rates. But again, that differs if I'm charging out in public, right? So again, this is the same slide that I showed last lecture as well. So if I'm charging at home at PG&E, I might be paying something like 36 cents per kilowatt hour. Whereas if I'm in Sacramento, I may be paying 12 cents per kilowatt hour. But if I'm charging in public, I might be paying something like 56 cents or 64 cents per kilowatt hour. So how do we calculate fueling costs for electricity? Let's consider the average electric car in the US, about 0.3 kilowatt hours per mile, with electricity prices of 30 cents per kilowatt hour. I can do a similar type of calculation here. So I have 30 cents per kilowatt hour times my 0.3 kilowatt hours per mile, just multiply by the efficiency. We cancel out the kilowatt hours, right? And then we get a rate of 9 cents per mile. Okay, and so in this particular example, these prices are roughly accurate for, I guess, California, maybe a little bit on the low end for electricity prices. But generally speaking, it's going to look something like this. So the average electric car costs as much to fuel up as like a Toyota Prius, but maybe half as much as your average gas car. Okay. Yeah, if you're interested in looking at this in more detail, there are these fueling cost calculators that you can use online. So this one is from fueleconomy.gov. You can actually put in your zip code, I believe, and it will calibrate to your electricity prices. And here it'll tell you how much you save compared to like an average car, or you can select it to compare across different cars. Yeah, and then it'll look at how much you save if you're charging, on specific rates, or if you're charging mainly in public. Yeah, so if you're actually interested in looking at this in more detail, you can do these like cross comparisons on this website. Okay. So that is in regards to fueling costs. The next one is maintenance costs. Yeah, and so generally speaking, maintenance costs tend to be quite a bit lower than gas cars, kind of across the board. So electric vehicles, remember, we don't have any of the maintenance that you might have for parts related to your gas engine drivetrain. So things like your timing belt that you have to change out, spark plugs, anything having to do with the transmission, the alternator, all of those components, which you would have to have some kind of maintenance and repair over the lifetime of your gas car, those just don't exist for EVs. And in fact, even the brakes tend to last quite a bit longer for electric vehicles compared to gas cars, because with EVs, you're doing a lot of regenerative braking, so you're not wearing down your brake pads as much. And that actually adds up quite a bit. So your maintenance costs for electric vehicles tends to be something like half that of what you would see for gas cars. You don't really need maintenance on the motor or the battery, and so the drivetrain of the vehicle tends to have almost no maintenance costs in comparison to the gas car. There is actually one thing that is maybe a little bit more expensive than a gas car, and that is tires. So for vehicles that only have one motor, actually when you're doing your brake regen, you're putting all of the braking friction onto two tires, as opposed to with gas cars, a lot of them are stopping on all four tires now. And so you'll tend to wear through your tires like mildly faster is what people have found with electric vehicles. And that's not the case if you have any electric vehicle that has motors on both drive shafts, so on all four wheels. Okay, any questions about that? Yeah, so insurance costs, I don't know if there's great studies that have looked at this yet. There's lots of online calculators where you can look at differences. And when I was kind of digging this up, it was pretty inconsistent in terms of whether the gas car insurance prices are higher or EVs were higher. You can see that in some cases, like over here, this particular website was saying that the comparable gas car to electric vehicle, the EV would almost always be 10 to 20% more expensive, whereas other sort of insurance sites are saying actually insurance for the electric vehicle is cheaper. So not a great sort of rule of thumb for insurance. What I would say is that in general, insurance prices are going to scale with the price of your vehicle, right? If you have a really expensive car, it's going to be more expensive to insure, because if you get into an accident, all else equal, there's going to be a bigger payout for that car compared to a cheaper car. And so since electric vehicles tend to be more expensive at the upfront price right now, insurance costs, I believe, should be higher. That is sort of a simplification, though, right? Because insurance thinks about other factors like risks associated with particular vehicles. And I'm not aware whether or not EVs have been deemed to be substantially, less risky or safer from the standpoint of insurance that would sort of normalize those costs. Okay. Any questions? Any of this? Okay. Last part of the sort of main portion of cost that we've been talking about, registration fees. So all cars in California have to pay these fees. So California Highway Patrol, your money goes towards funding CHP. There's a transportation improvement fee based on the value of your vehicle, so that might actually be a little bit higher for EVs. There's a fixed license fee that's also calibrated to the vehicle price. And then you may have like local fees. Those are going to be, I would say, generally kind of similar between gas cars and electric vehicles. But we actually do have an EV-specific fee known as the road improvement fee, where electric vehicles have to pay an extra registration fee simply for being electric. This is actually maybe somewhat of a controversial topic. We're going to talk about this a lot more at the end of class when we think about sort of some of the EV-specific policies. But what I'll mention just right now is the idea behind this fee is to replace the gas tax. Okay, so if you are driving around in the state of California and you're using any of our roadways, a lot of those roadways and highways and freeways, the funding for building those roads comes from essentially gas taxes. Okay, and so think about what that means for an electric vehicle. You never fill up on gas, which means you never really contribute to that pot of money that's meant to go into building out our roads. We'll talk about kind of the fairness of all of that later, but the idea behind this fee is a replacement for that gas tax. Part of the reason why this is controversial is, with a gas tax, generally speaking, the more that I drive, AKA the more that I use my roads, the more I pay for those roads, right? Because the more I drive, the more gas I have to use. One of the reasons why this fee is controversial is that it's a flat fee that ignores how much you actually use the roads. So if I'm an electric vehicle owner, I could drive 0 miles a year, or I could drive 50,000 miles a year, and I would pay the same amount of money. Okay? So we'll touch on that topic a lot more later on. Other costs that could show up in your ownership costs, things like tolls, things associated with parking. There, EVs actually benefit a little bit. You may have some EV exempt parking where you don't have to pay a fee, or you get better parking spots, that sort of thing. But generally speaking, people rarely include these costs in that TCO, usually because it's a wash, and also because data for this type of thing would be really cumbersome to get. Okay, so that's kind of the landscape of costs for that go into the total cost of ownership. Anyone have any questions about that? Yes.
When it comes to electricity costs,
Yep.
do you get any sort of benefits for households that have solar panels and that?
Yes. So they don't directly have to do with you owning an EV, although I will say if you do own an EV, you could actually subscribe to a different rate structure, which could benefit you. But yeah, if you own solar panels, putting aside all the economics with that, when you self-generate that electricity, in general, that's going to be a lot cheaper. So that could bring down the costs, the total cost of ownership with your electric vehicle for sure, because your fuel price portion could shrink quite a bit. But you have to balance that against the economics of buying the solar panel, and that's a whole separate question. But in general, I would say in California, the co-ownership of solar and EV tends to be very economically beneficial for that owner. Don't know how much to get into this, but I will say, not necessarily for everyone else in the state of California. The way that you get some of the benefits for solar kind of makes everyone else pay more money to some extent, because I don't know if anyone's ever looked at their electricity bills, but the idea is if you look at your electricity bill, you pay for the cost of generating that electricity, but you also pay for a lot of the fixed infrastructure, like the transmission lines and the distribution lines and all of that infrastructure. When you have solar, you get to any electricity that you generate directly decreases all of your contributions to all of those things, but the utility still requires that infrastructure to be paid for. So what ends up happening is everyone else pays more. So people who own solar panels in California are subsidized by people who don't own solar panels in California. So there's a separate equity issue there that's important to think about. What was that? Yes, yeah. So we were talking about you have a totally disconnected. Yeah. So you that wouldn't apply for someone who's like grid defected, which means that you're not connected to the grid. Yes. Sorry, I think it's too loud. I can't hear you. Okay. Oh, okay. So costs related to like air conditioning or decreased efficiency due to lower weather or colder weather. Yeah. So that would all of that would play into in this part of the calculation. I have this number 0.3 kilowatt hours per mile as a catch-all for the average efficiency of the electric vehicle. If I'm aggressively using air conditioning or I'm having to heat the car a lot more, you may modify that 0.3 kilowatt hours per mile, right, to account for that. So if you say, well, on average, the efficiency is 0.3 kilowatt hours per mile, but I live in New England where it's really cold and my efficiency goes down, maybe I should calculate that with like a 0.35 or 0.4 kilowatt hours per mile. And so this would be where you would make that adjustment. Yeah. Okay, any other questions? Yeah. Uh-huh.
Did they make it a flat fee versus just charging it as they do with like gas cars? Like why did that happen?
Ah, yes. uh, yeah, well, so I've done a lot of work in this area, and there's a lot to talk about. We'll get into a lot more detail on this later, but I will just mention for now is that uh, it's an implementation issue. So if we could, I think we would, but think about the way gas taxes are levied. So with a gas tax, it's actually really simple. Before your gas gets to a gas station, it comes from a giant storage facility called a bulk storage terminal. Does anyone know how many bulk storage terminals there are in the state of California? Any ideas? I believe right now there's 33. That means if I am the government, I can essentially go to 30 different entities and collect taxes, right? So think about how efficient it is for me to collect taxes and the cost associated with doing that. Okay, now, if you want to do something similar for electric cars, well, the point of collection isn't so simple, right? Because we do produce electricity, but it's from many more sources, and we don't only use electricity for cars. We use it for TVs and lights and so on, right? And so to actually track what goes into your car, you'd probably need to do it at the meter. And you'd need like a separate meter for cars, which actually just doesn't really exist. And if you did do that, it would be really expensive. And there's a whole set of logistical issues with doing that as well, which we'll talk about later. So, long story short, the implementation for doing that collection is like way harder for cars. The road improvement fee is kind of convenient in that all these fees are collected by the DMV, and so they just say, okay, we're just gonna tack on this extra thing. You're already doing it, so it's not gonna like cost more money to implement the program. So that's kind of the simple answer. Yeah. Okay, any other questions? Okay, so the last thing I'm going to talk about And this may also run a little bit into next class, depending on how far we get into this. But we should be able to catch up after next class. Okay, so I've been talking about this idea of like total cost of ownership, and kind of comparing the math between looking at that TCO for gas cars versus TCO for EVs. When we think about the way that people actually behave and the way that we value those costs that I was just talking about is actually a little bit different. So this comes to a more broad concept about valuing things over time, which we'll explore now. So this is the idea of time discounting, which describes a preference for value of things today versus value of things tomorrow. Okay, so is money worth more to you now or in the future? So let's say I have $100 and I'm gonna give you guys all $100 either today or 1 year from now. So raise your hand if you would want that money today. $100 today. Okay, and raise your hand if you would want it 1 year from now. Okay, like one person. Yeah, so generally speaking, people have a preference for taking that money today. Just curious, why would you take the money a year from now?
I don't really need $100 today,
Okay,
but
you might need
a year
it.
from now, I'll probably forget that you were gonna give me
So you're like, surprise, oh, I got this 100, yeah, right. But what I would say is that if you wanted to do that, like you could always take that $100 and like stick it in a bank account and get some interest. And then a year from now, you'll have more than $100, right? So related to time discounting is like the value of what you think you could do with that money and whether or not that could like actually lead to higher gains in the future, right? So like taking that money and sticking it into a bank account at the like lowest bar, you're probably making at least what you get out of like interest, right? And so you'd probably need to get offered, you know, $110 or something next year in order to want that, right? So anyways, this idea of time discounting means that the way that I value like cheaper fuel costs from electric vehicles compared to the higher upfront price of buying the car is actually going to be a little bit different. Yeah, okay, so if I have some money today, it's actually worth less to me a year from now and so on and so forth because of this idea that we have these like discount rates, okay? And so I can calculate the value in some future year based on the discount rate and the number of years into the future that I'm looking at. So I is essentially the discount rate. So with a 5% discount rate, then $100 today would be worth something like $95.5 a year from now, and in 5 years, $100 today would be only worth like $78 in 5 years. So if I were to take that $100 and look at the value of that over time, it would look something like this at a 5% discount rate. Okay. So what discount rate should be used? There isn't necessarily a right answer. Different entities will have different discount rates. So businesses often use like a 10 to 15% discount rate. A regulated utility might be required to use like a 6% discount rate in their calculations. Generally speaking, higher the risk, the higher the discount rate. When we think about the way people value fuel savings, for example, oftentimes we see something on the order of like 2 to 5%, which is kind of close to the way that like us as individuals often are discount rates that are elicited from us. That's kind of the range that we see for individuals. Okay. Okay, so I have a couple of examples kind of going through the calculation of TCOs once we add in the discount rates. But actually, I'm going to do this next time because we need time for our quizzes. So I'll end here for today, and we're gonna pick up, I'll do a quick refresher on discount rates, and then we'll go through some of these examples doing the calculations. Okay? All right, so yes, put everything away in preparation for the quiz, which will go out right now, and you are welcome to go ahead and start as you receive the quiz. Oh.
Sorry about that.
We'll put the quizzes up here.
I have a question.
Yeah.
This right here, I mean, I guess I'm misunderstanding because they are calculated differently, like inverse. So is that,
I would say that's not like the
Or just not
primary
non-linear?
thing.